Hello, this is Yashveen. Today I'm going to be solving paper 4 variant 2 October November 2019 0625 physics. Starting with question number 1, figure 1.1 is the top view of a rectangular paddling pool of constant depth. The pool is filled with seawater. A. The volume of seawater in the pool is 264 meter cube. Calculate the depth of the pool. Alright, so the formula of volume is length into breadth into height. So here we need to find out the depth, which is also known as the height. Height here is equal to volume 264 divided by the length into breadth, which is 44 into 2. So this is equal to 264 divided by 880, which gives us the depth as 0.3 meters. B. The mass of the seawater in the pool is 2.7 into 10 to the power of 5 kg. Calculate the density of the seawater. Give your answer to three significant figures. Alright, so density is equal to mass divided by volume. Mass in the question is 2.7 into 10 to the power of 5 divided by the volume, which is also given in the question, is 264. And this gives the answer as 1020 kg per meter cube. C. Calculate the pressure due to the seawater at the bottom of the pool. The pressure is equal to density into gravity into height. Density calculated in the previous part is 1020, but I'm going to be using the actual value, which was 1023 into 10 into height, which is 0.3, and that gives the answer as 3100 pascals. D. State a suitable instrument for measuring the dimensions given in figure 1.1. That can be a measuring tape. Question number 2. A. State the two conditions which must be true for an object to be in equilibrium. Alright, so there should be no resultant forces and clockwise moment should be equal to anti-clockwise moment. B. Figure 2.1 shows a uniform meter rule PQ in equilibrium. The distance PQ is 100 centimeters. The mass of the rule is 0.12 kg and its weight is W. 1 on figure 2.1. Draw and label an arrow to show the force W acting on PQ at the center of the mass. So the center of the mass is going to be the center of the scale over here, which is 50 centimeters mark. And here we have W. 2, an arrow to show the force R acting on PQ at the pivot. So the pivot has a force acting upward, and here it is.
Part 2. By taking moments about point P, calculate F. About the pivot means pivot is the turning point, and you have to take all the perpendicular distances from the pivot. So the rule is total clockwise moment is equals to total anti-clockwise moment. From the pivot, our clockwise moment will be the rule's weight, 0.12 into 10 multiplied by the perpendicular distance between the point W and the pivot, which is 0.4 meters. And this is equal to anti-clockwise moment. There are two weights which are causing anti-clockwise moment. The first one is force F and the second one is P. So the first one will take F multiplied by the perpendicular distance between force F and the pivot, which is 0.9 meters. And then there is additional force which will result in anti-clockwise moment, which is 0.5 newtons multiplied by the perpendicular distance between P and pivot, which is 0.1 meters. So force F has a magnitude of 0.48 newtons.
3. Calculate R. So R is part of the upward forces. R and F are acting as the upward forces, and the downward forces are the weight and 0.5 newtons. And since this rule is in equilibrium, upward force should be equal to downward force. So the upward forces acting are R plus F should be equal to the weight plus 0.5. And so R is going to be equal to weight, which is 1.2 plus 0.5 minus F, which is 0.48, and that is equal to 1.22 newtons. Question number 3. Figure 3.1 shows a gas contained in a cylinder enclosed by a piston. A. Describe in terms of momentum of molecules how a pressure is exerted on the walls of the cylinder. Alright, so whenever you come across this term momentum while describing the pressure, the answer is always a given. So you must write 3 points over here, which give the 3 marks. The second statement is and the third one is so a bit of explanation over here. When molecules move and collide with the walls of the container, change of momentum results in force. Change of momentum is basically mv minus mu, which divided by the time is equal to force. So this is how a change in momentum results in force, and pressure is equal to force upon area. So force and pressure are directly proportional. So once force is exerted, pressure is also exerted. The piston is pushed into the cylinder. The volume decreases from 820 centimeter cube to 330 centimeter cube. The pressure gauge measures the pressure after compressions as 20,000 pascals. The temperature remains constant. Calculate the value of the pressure before the gas was compressed. Alright, so we have the formula here. P1V1 is equal to P2V2 according to Boyle's law, since temperature is constant, and we need to find out the pressure, which was the initial pressure of the gas. And we have the final pressure as 20,000 multiplied by the final volume, which is 330, divided by initial value of volume, and this is equal to 8,000 pascals, which is the initial pressure. Question number 4a. A student carries out an experiment to determine the thermal capacity of a metal block. The block is heated by an electrical heater for 23 minutes. The current in the heater is 3 amperes at a potential difference of 12 volts. The temperature of the block rises from 20 degrees Celsius to 70 degrees Celsius. Calculate the thermal capacity of the block. Alright, so since this is not specific heat capacity, it's only thermal capacity, we don't need to add the mass over here. So the formula of thermal capacity is energy divided by change in temperature. So energy here is not given, right? So the formula of energy here is power into time, which is equal to voltage into current into time, since power is also not given. So power here is energy here is equal to voltage, which is 12, into current, which is 3, and time, which is 23 minutes. So we'll have to convert minutes to seconds, which is 23 into 60. And this gives the answer of energy as 49,680 joules. And then change in temperature is equal to 70 minus 20, which is equal to 50 degrees Celsius. So we have the thermal capacity as 49,680 divided by 50, and that gives the answer as 990 joules per degree Celsius. B1. Two metal spheres of different diameters are heated to 900 degrees Celsius in a hot oven. The two spheres are removed from the oven. State and explain any differences in the initial rates of emission of radiation of thermal energy between the two spheres. Alright, so we have, due to larger surface area, the sphere with larger diameter has greater rate of radiation. 2. One hot sphere is now heated in a hotter oven. State and explain any effect on the rate of emission of radiation of thermal energy from that sphere when it is removed from the hotter oven. Alright, so the rate of reaction over here would be greater since heat inside the sphere is greater. Question number 5a. One difference between longitudinal wave and a transverse wave is that a longitudinal wave consists of compressions and rarefactions. 1. Explain the terms compressions and rarefaction using ideas about particles. Alright, so we can either use particles or pressure to differentiate between compressions and rarefactions, but since here the question is only asking about the idea of particles, we need to stick to that rule. So compressions are area where particles are closer together. And rarefactions are exact opposite of that. To describe one way in which longitudinal wave motion differs from transverse wave motion. Right, so here vibrations are parallel to direction of wave motion. And here the directions vibrations are perpendicular. B1. A sound wave of frequency 0.120 kHz travels through a rock at a speed of 3500 meters per second. Calculate the wavelength of the wave. So first I'll start by converting kilohertz to hertz, and I'll multiply it with 1000 to do that, which gives the answer as 120 hertz. The formula of wavelength is equal to speed divided by frequency, and that is equal to 3500 divided by 120, which is equal to 29 meters. The wave travels from the rock into the air. State and explain whether the wave will be audible to a healthy human ear. Alright, so the wavelength might change, but the frequency does not change. And the frequency would so remain 120 Hz, which is between the audible range of 20 Hz and 20 kHz. So yes, it is audible. Question number 6. A. Figure 6.1 shows an empty container and an observer's eye. There is a small coin at position O. The observer is unable to see the coin. The observer and the coin stay in the same position and the container is filled with water. The observer can now see the coin. 1. Explain why the coin can be seen by the observer. So I'll draw a diagram, a part of the diagram over here, which would make it easier for me to explain. Right, so suppose we have the normal over here, and that would mean the refractive ray would bend away from the normal because it is traveling from a denser medium to a rarer medium. So angle of refraction is supposed to be greater than angle of incidence. And that would mean the refractive ray would be closer to the vision of the person's eye than when it was before water was present in the container. So that makes it easier for the person or possible for the person to be able to see the coin. To state the name of the wave process which occurs at the light as the light passes from water into the air. This is refraction. 3. Explain why the image of the coin is a virtual image because it can't be captured on a screen. B. State the speed of light in air. Alright, that is 3 into 10 to the power of 8 meters per second. C. The refractive index of water is 1.3. Calculate the speed of light in water. So refractive index is equal to speed of light in vacuum or air divided by speed of light in any substance, which means speed of light in water should be equal to speed of light in air divided by the refractive index, and that is equal to 3 into 10 to the power of 8 divided by refractive index given in the question is 1.3, and this gives us the answer as 2.3 into 10 to the power of 8 meters per second. Question 7a. Figure 7.1 shows a coil of wire around a thin plastic cylinder. The plastic has no effect on any magnetic field. The galvanometer is extremely sensitive. A magnet is fixed to a small trolley that runs without friction on a track through the cylinder and coil. 1. The trolley is released from point A, so it runs through the coil from right to left. State and explain what is observed on the galvanometer. Alright, so this magnet has magnetic field around it, and once that field is cut by these these turns of coils, it induces an EMF in the coil, and that is detected by the galvanometer. But here the magnet is going to be moving across throughout the coil, and this question is going to be using Lenz's law. And according to Lenz's law, an induced current, which is going to be induced when the magnetic field lines of this magnet are going to be cut by the coil. So the induced current always flows in a direction such that it opposes the change producing it. Once a current is induced over here, the coil is also going to be having poles. It's going to be having um, some uh, some amount of magnetic field around it, and to oppose the movement of this magnet going through it, while magnet is entering the coil would be having south pole over here, so that these like two poles would be repelled, but it would keep moving. And this is happening because, once again, I'd like to remind that according to Lenz's law, induced current always flows in a direction such that it opposes the change producing it. So basically, the movement of this magnet is the change, and it's producing the current. And that current in turn gives a magnetic field to the coil, and this would also then have south and north poles. Once it enters, it is going to be opposing the movement of the magnet, so it would oppose its entrance into the coil, and that can be done by having this end of the coil as south pole, so it would repel the like pole, which is south over here. And while the magnet leaves, current in the induced current in this coil would try to attract it so that it opposes the motion of the magnet. And so by doing that, it would create south pole over here while the magnet is moving out. So going in, south pole is over here, moving out, south pole is induced over here. But regardless, the magnet moves throughout. The only thing over here is that the magnetic field produced around the coil opposes the movement of this magnet. So you see, the as the poles of the magnetic field in this coil are reversed, the direction of current also reverses, and because of that, the deflection of galvanometer reverses. It keeps changing. Suppose it moves right while the magnet is moving, it would move towards left while the magnet leaves. So we have the answer as a deflection is observed due to change in magnetic field. And when I say change in magnetic field, I mean the magnetic field of around the coil, which changes its pole, and so the direction of current also changes, which causes deflection in opposite directions of the galvanometer. 2. The trolley is now released from point B, so it runs through the coil from right to left again. State what is observed on the galvanometer and explain why it is different to your answer in A1. So once it is released from a higher position, its acceleration is going to be greater, and everything else pretty much remains the same. So once it speeds through the plastic cylinder at a faster speed, the deflection would be greater or faster, and it would also last for a shorter time. B. Figure 7.2 shows an extension lead used to supply power to a 3 kilowatts electric heater on a cool evening. State and explain three dangers with this arrangement. Alright, so we have damp grass over here which can cause electrocution. Again, the cut in insulation can also cause electrocution. And the third one can be overheating of the lead over here because it can sustain 25 watts. However, the electric heater needs 3 kilowatts, so this is going to be quite a burden on the lead.
Question number 8, part A. A wire of length 2 meters and cross-sectional area 0.4 millimeters square has a resistance of 0.14 ohms. Calculate the resistance of another wire of the same material of length 3 meters and cross-sectional area 0.9 millimeters square. So the formula related to this question is resistance is equals to resistivity multiplied by the length, and that is divided by the cross-sectional area. This whole will be divided by the cross-sectional area. Alright, so there is one quantity which will have to remain common since we are using two different wires of the same material, and that quantity is resistivity. So we'll make resistivity the subject of the formula. So resistivity is equals to resistance multiplied by the cross-sectional area, and the whole will be divided by its length. Now we'll equate both the equations. Resistivity will remain common in both the equations, so we can equate them in terms of resistance, area and length. Resistance 1 multiplied by area 1 divided by length 1 is equals to resistance 2 into area 2 divided by length 2. So our resistance 1 is 0.14 ohms from here. So 0.14 ohms multiplied by our first area was 0.4 millimeters square. Now we have to convert this millimeter square to meter square, and that will become 4 into 10 to the power negative 7. We'll divide all this by our first length, which is 2 meters. 2. This is equals to our second resistance, which is not given to us, and that's what we have to calculate, so we'll take it as it is, multiplied by our second area, which is 9.9 millimeters square, and we have to convert this millimeter square to meter square too. So this will become 9 into 10 to the power negative 7. This whole will be divided by our second length, which is 3 meters, 3. And that's how we'll calculate the second resistance, which is equal to 0.093 ohms.
B. A student is designing a digital electronic circuit. Figure 8.1 shows her partly completed design. Okay. 1. Table 8.1 is a truth table. Complete the columns in this truth table to show the values for input B in the circuit. Okay. So here we have input B and input A, which are going to lead towards input C. As you can see over here, input C is a NOR gate, which means it would have exact opposite outputs as we would have in OR gate. And OR gate has 4 cases, and three of those 4 cases would always have the output 1. That is when the inputs are 0, 1, 1, 0, or 1, 1. So these 3 inputs give the output as 1, and the only case in which the output is 0 is when both of the inputs are 0. And since this is going to be the opposite of OR gate, we'll have the opposite cases, and 1 would only be the result of both of the inputs being 0. The rest would be 0, and the rest of the cases should have at least 1. And the rest of the cases should have 1 in them, so that it would be opposite case of an OR gate. 2. The column O on the truth table shows the desired output values for the circuit. On figure 8.1, complete the circuit to achieve these output values. Label any gate used. Okay, so as we can see over here, this is also an a NOR gate, because the only output in which we have 1 over here is when both of the inputs are 0, the complete opposite of an OR gate, because 0 1 is also giving 0, 1 0 is also giving 0, which in the case of OR would have been 1 and 1 over here, 0 and 0. So I'll draw a NOR gate over here, which is the opposite of an OR gate. Here is NOR gate. Question number 9a. Describe what is meant by the term electric field. It is the area where a charge experiences a force. B. Figure 9.1 shows two parallel conducting plates connected to a battery. On figure 9.1, show 5 lines to show the electric field pattern between the two plates. C. When fully charged, a 1.2 volt rechargeable battery can deliver a current of 210 milliamperes for 10 hours. 1. Calculate the charge that can be delivered by the fully charged battery. Alright, so first I'll start by converting 210 milliamperes to amperes by dividing it by 1000, and that gives the answer as 0.21 amperes. Since charge is equal to current into time, we have current as 0.21, and time should also be in standard unit, which is 10 into 3600, which converts 10 hours into seconds, and this gives the answer as 7600 coulombs. 2. Calculate the energy stored in the battery when fully charged. Alright, so the formula of energy is charge into voltage, which is equal to 7600 into the voltage, which is 1.2, and that is equal to 9100 joules. 3. State the type of energy stored when the battery is charged. This is a chemical energy form. Question number 10. A. The nucleus of a hydrogen atom is a proton. The mass of a proton is m, and the size of charge on a proton is E. Complete table 10.1. Express your answer in terms of m and E. 3 spaces have already been completed. Alright, so we have particles or emissions, mass, and their charges. Proton has a mass of m and neutron has an equal mass. It does not, however, have any charge, so that is going to be 0. It does not have mass either, nor does it have any charge. Nucleus of helium has 2 protons and 2 neutrons, and since both of them have equal masses, both of them are going to be having m into 4, which is 4m of mass. Charge is going to be 2e, since there are 2 protons and no electrons. B. Many schools and colleges use radioactive isotopes for teaching and research. Describe how these radioactive isotopes are handled, used, and stored in a safe way. Right, so they are handled using tongs and gloves for limited times. and stored in lead containers. Since lead is not penetrable by most of the radioactive isotopes. Alright, so we are completed with this paper. Thank you for watching.